Okay, just as a reminder, when your second derivative is negative, it means your original function is concave down. When your second derivative is positive, it means your original function is concave up. If your second derivative changes either from negative to positive or from positive to negative, then the point where it changes is going to be called the inflection point, as long as there's a tangent slope at that point. The tangent slope can be a vertical tangent slope, but the tangent slope has to exist. Okay, for this example, we have to put these in order. We're looking at the graph of f. You have to see which one is bigger. It looks like f of 3 is 0, so that's usually in the middle. And then one of these is going to be positive and one's going to be negative. Because our function is increasing, that means our first derivative should be positive. So we'll put the first derivative on the right side. And because our curvature is concave down, that means our second derivative is going to be negative. So that's going to go in the front. Okay, so we're saying the second derivative is less than the value of the function, which is less than the value of the first derivative at x equals 3. The reason we know that is because f of 3 is 0, f prime of 3 is positive, and f double prime of 3 is negative. So this one was kind of like a little puzzle. We just had to put it in order. Okay, for this example, we're going to have to choose between these two tables. We're looking for something that has a first derivative that's negative. Remember, if your first derivative is negative, that means your original function is decreasing. So that's the first thing we're looking for. Which one of these is decreasing? This one is 10, then 9, then 7, then 3. So that one's good. This one's 10, then 6, then 4, then 3. Yes, they're both decreasing. Now we got to look for this. This one's a little bit harder. We need the second derivative to be greater than 0. So that means concave up. So we need something that's decreasing and concave up. We're looking for this kind of picture here. Decreasing and concave up. Okay, let's go take a look. A couple examples. The first example is going to be the red one. Let's go look at this red one here. Okay, for this red one, you can see when you have 0, 10, and then you go to 1, 9, you've decreased by 1. And then when you go to the next point, you're going to decrease by 2, and then you're going to decrease by 4. So for this one, we're decreasing by more every time. And when you decrease by more every time, you end up being concave down. So that's not what we want. We're looking for concave up. So let's look at the blue example. Okay, for this example, you'll notice we decrease by 4, then we decrease by 2, and then we only decrease by 1. So we're decreasing, but we're decreasing by less every time. When you do that, you end up with decreasing concave up. And that's exactly what we're looking for. So our answer is going to be the blue table. The blue table is decreasing, but it's decreasing by less every time. At first, it decreases by 4, but then it only decreases by 2, and then it only decreases by 1. So that's going to be decreasing by less every time. So that's decreasing and concave up. Final answer is the blue table. Okay, for this example, we want to know which point satisfies these two conditions over here. The first condition says your first derivative is negative. That means we need to be decreasing. Well, we know we're decreasing at point C, so C is one of the possibilities. And we know we're decreasing at point D. That's another possibility. For this example, it looks like the inflection point is somewhere around here. So we're just estimating the inflection point. Now I want you to notice at point D, we are concave up. So I'm going to put a CU for concave up. And I want you to notice at point C, we're concave down. So I'm going to put a CD there for concave down. We need our second derivative to be positive, so that means concave up. So it cannot be point C. Point C is concave down, so our correct answer is going to be point D. So I would choose point D. For this example, they want us to say which x values have inflection points for the original function f. Now, they didn't give us a graph of f, so you got to be really careful. This is a graph of f double prime, so this is the second derivative. Now, what I want you to notice is that the second derivative is positive when it's above the x-axis. So that's where the second derivative is positive. The second derivative is negative when it's below the x-axis. And the second derivative is 0 at the points that I'm touching right now. So those 3 points are going to be kind of like critical numbers. That's where your second derivative is 0. Now let's fill out our chart. Our second derivative is positive before you get to -2 and after x equals 5. Our second derivative is negative in between. Again, we're looking for the x values for the inflection points of the original function. So we need our second derivative to change signs. That does not happen at x equals 1, but it does happen at x equals -2 and at x equals +5. So those are the two inflection points. That's where we change from either concave up to concave down, or from concave down to concave up. Again, this can be really tricky because we're not looking at the original function f. We're looking at the second derivative. And we use the second derivative to describe the original function f. A lot of people get tricked on this question because they treat that graph as if it was f, but it's not. It's f double prime. So our final answers is there's an inflection point at x equals -2, and there's an inflection point at x equals +5. But it's the graph of f that has the inflection points, not this graph right here. Okay, this is the same question, but the thing is that we're pretending that this graph is f prime. So the example we just looked at, we were looking at the graph of f double prime, but what if this graph was f prime? What would that mean about inflection points of the original function? Well, we still need to figure out f double prime by looking at this graph. What is f double prime? Well, f double prime is the derivative of f prime. Another way of saying it is the slope of f prime. What I want you to notice about the slope of f prime is that that's the second derivative. So the second derivative is the slope of this graph here. You'll notice the slope is negative, then the slope is positive, then the slope is negative again all the way till here, and then the slope is positive afterwards. So those pluses and minuses are the slope of this graph. And remember, the slope of this graph is the same thing as the derivative of this graph. So those little pluses and minuses are the derivative of f prime, and so those little pluses and minuses are the same thing as f double prime. So that means f double prime is negative until you get to -1. And then f double prime is positive until you get to +1. And then f double prime is negative until you get to 4. And then f double prime is positive afterwards. And that means our original function is going to be concave down until you get to -1, and then concave up until you get to +1, and then concave down until you get to 4, and then concave up afterwards. So we actually have 3 inflection points for our original function f. Here they just want to know what are the x values for those inflection points, and these are those 3 x values. Again, you have to change signs either from negative to positive or from positive to negative. And you can see that that happens at all 3 of those x values. Our second derivative changes polarity from either negative to positive or positive to negative. And so those are the 3 x values of the inflection points for the original function f. Okay, for this example, they're giving us f prime again. We're pretending that this is f prime. You'll notice it's the same graph we used for f double prime a couple examples ago. But now, if this was the graph of f prime, what does that tell us about f? If we were looking for the absolute max, could we use this graph of f prime to find the absolute max of f? Well, if I was doing the first derivative test, I would want to know the values of f prime, and I would start with those critical numbers. That's where the first derivative is 0, or where the first derivative is undefined. We don't have any spots where the first derivative is undefined, but our first derivative is 0 at -2, 1, and 5. So those are going to be our critical numbers. Now, when you're above the x-axis, you're positive. So our first derivative is positive here and positive here. When you're below the x-axis, you're negative. So our first derivative is negative right here. Now let's fill out the chart. Our first derivative is going to be positive before x equals -2, and our first derivative is going to be positive after x equals 5. Then our first derivative is going to be negative between -2 and 1, and also between 1 and 5. So that means our original function is going to be increasing until you get to -2, then decreasing all the way to 5, and increasing again after x equals 5. We are looking for an absolute maximum value. So we're on a closed interval. It's either going to happen at the endpoints, so it could happen over here, or the absolute max could also happen at x equals -2. Now we do have to figure out which one of these is going to be higher, because we're looking for an absolute maximum. Which one of those 2 points is higher? Now here's how we're going to figure it out. If you look at the area below the curve, that's how much it's going to increase or decrease. So you can see for that first part, the area is extremely small. So we increase an extremely small amount. Then we decrease that much, and we decrease that much, then we increase this much. So what we're doing is we're increasing a really small amount, and then we're decreasing a whole lot, and then we're increasing a really small amount again. And we're asking which one of those is an absolute maximum. Is it this spot here, which is x equals -2, or is it the end point over here, which it looks like it's x equals 5.2 or something like that? In this situation, it's not the end point. It's going to be x equals -2. That's the highest point. And so the absolute max will happen at x equals -2. So that's something new that we kind of learned just now. We've never learned that before. The area under the curve is how much it increased. So if the area was 1, then it increased by 1. If the area was 10 and you're below the x-axis, then that's how much you decrease. You decrease by 10. For this example, we increased a really small amount. We're saying increased because our derivative is positive. Then we decreased a large amount. That's what this part is in the middle. And we increased again a really small amount. And that helps us determine which one of these 2 points is the absolute maximum. Is it this point here at the top, or is it the end point over here? And for this example, it was that point at the top at x equals -2. So the x value of the absolute max is x equals -2. We can't actually find the y value because we don't have the original function. But for this example, all they wanted to know is what values of x. And so the value of x that has the absolute max is x equals -2. Okay, we need to start off by noticing that this is the graph of f prime. So this is the derivative. Here they want us to find the equation of the tangent line to the graph of g at x equals 4. In order to find the equation of a tangent line, we're going to need a point and we're going to need a slope. In order to find the point, we have to plug in 4 into our g of x function and see what g of 4 is going to equal. If we plug in 4, we get 3 times 4 times f of 4. The good news is they do tell us what f of 4 is equal to. F of 4 is equal to 2, so we can plug that in. So we get that g of 4 is equal to 24, and so that's going to be our point. It's a point that lands on the g function. When you plug in x equals 4, you get 24 for the y value. So the equation of the tangent line that we're looking for is a tangent line on the graph of g. Okay, let me put my point over here in the bottom left. Our point is 4, 24. Remember, that's a point that lands on the graph of g. Okay, now all we need is the slope, and then we're done. In order to find the slope, I need the derivative, so let me do g prime. Looks like we have the product rule. It's going to be the first times the derivative of the second plus the second times the derivative of the first. We need to evaluate this derivative at x equals 4, and that'll tell us the slope that we need when x is 4. Now there are 2 missing values. I need to know what f of 4 is. Remember, that was given. That's just a 2. And I also need to know what f prime of 4 is. We can get that from the graph. This is the graph of f prime of x. So when x is 4, you can see we have -60. Okay, final answer for our slope is going to be -714. I'll write that in the bottom left. It's kind of a big number. But now we can find the equation of our tangent line. We just need to use the information we found in the bottom left corner here. It's going to be y minus 24 equals m times x minus 4. Now you could stop right there. That would be your final answer. Or if you want to solve for y, you would get this. And that's it. Again, you're trying to find the equation of a tangent line. Don't get stressed out. It's just the equation of a line. But it's not the tangent line on the graph of f. It's a tangent line on the graph of g. So you first need a point for g. So you plug in x equals 4 into your g function, and that gave us 24. So we had our point, and we needed the slope for the g function. So that's the derivative. And we plug in 4 into that. There were two weird values we had to figure out. One of them they gave us, f of 4 was 2. The other one we had to figure out, and that was f prime of 4, and that was negative 60. Now, some people will make a mistake, and they'll use negative 60 as their slope for the equation of the tangent line on g. But remember, negative 60 is the slope for the f function, so that's not going to be your slope for the g function. And that's it.